So let's go back to our estimate of phi x. So phi x equals the norm of f square subtract the twice of the sum and plus the sum of xi square. Then we see that the partial derivative of phi x is the first term has nothing to do with xi, therefore it is 0. The second term, taking partial derivative with xi, give you 2 minus 2 fei. Okay, and the last term, xi square, sum of xi square partial derivative with xi will give you 2xi. So let's have a look on this function phi. This term is the first order term. The first term is constant with respect to x. The f non-square term is constant. And this term is the first order term with respect to the variable x. And the last term is second order term. Therefore, from this you can see that phi x goes to positive infinity if the norm of x goes to infinity. Okay, the function phi behave in this way, going up. So it has a minimum point as a continuous function. Going to positive infinity at infinity, it must attempt its minimum point somewhere. And the minimum point, the partial derivative should be 0, right? Because f is obviously continuously differentiable. Phi is obviously continuously differentiable. So the minimum point must be 0. Therefore, at the minimum point, this is 0. This is 0 tell us that xi should be fei. That is to say, when g equal the sum of fei I from 1 to n, when g equal to this element, when g equal to the projection of f on xn, the distance from f to g obtained is minimum, attains is minimum. Okay, so this proves the conclusion of this lemma. The conclusion of this lemma is precisely that the distance from f to the projection is the minimum of is the infiniment of f to distance from f to g in xn. But now our argument shows you that if and only if g is the projection, we attain the minimum. Okay, so this proves our result. And also, our proof will also tell you that this infiniment is attained, and attained at a single point. The single point is precisely the projection of f on xn. Okay. Now, we make some computation. We compute f minus fn. What's this? So this is fn minus the inner product of fn, which itself, that is the norm of fn. So what's fn? Fn is the sum I from 1 to n, ci ei. Here, ci is the inner product of f and ei. Okay, so so the norm of f square, so this is f summing up ci ei I from 1 to n, subtract the norm of fn, that is ci ei I from 1 to n c j e j. You can also represent fn by c j e j. Using another letter to denote the summation is okay. Okay. Now this is the sum of ci fei, the first term. The second term using the trick, you see that is I from 1 to n ci ei j from 1 c j e j. But for this, you see that if j is not equal to I, the result is 0. Okay, because ei and ej are orthogonal, also normal. So only the term j equal to I exists. So this gives us ci fei is ci, so ci square. Subtract the sum ci. So when this part can only know 0, the terms in this sum, only the term j equal to I is non-zero. When j equal to I, this gives us ci ei. Ci ei making inner product with ei here give you ci. Therefore, this is also ci square, and the result is 0. So this means that f subtract its projection is orthogonal with fn. Okay, geometrically, this is xn, this is f, and this is our fn, and this is precisely f subtract fn. It is orthogonal to fn. So our computation justified this intuitive conclusion from geometric consideration. Okay. Now, having verified that these are orthogonal, we can apply the Pythagoras theorem. The norm of f square is the norm of f minus fn, then plus fn square. But these two terms are orthogonal, as we just verified. Then by Pythagoras theorem, this is the norm of f minus fn square plus the norm of fn square. Okay. Of course, this is not less than the norm of fn square, which is the sum of ci square. In our proof of this orthogonal relation, we have obtained the result that the norm of fn square equal the sum of ci square. Okay, we have proved this in our computation. So we have this equality. And we also write the ci square in a more precise form, that is inner product of f and ei square. So we obtained this result. For every n, this is true. This argument is true for every n. So we have the so-called Bessel inequality. Bessel inequality. This is the theorem. let EI be an orthonormal system in X, and F in X. Then we have I from 1 to n inner product of F and EI square less than or equal to the norm of F square. This is called Bessel inequality. Now we have proved this inequality because we have proved that for every n here, the sum of the first item of the FEI, okay, of the square of the inner product of F and EI will not greater than the norm of F square, the square of the norm of F. This is true for every n. This means that the partial sum of this series is, we have proved that for any n. Okay, we just proved this result. So this means that the partial sum of this series is bounded about by the norm, the square of the norm of F. So because this is a non-negative series, every term is non-negative. So this means that the series is converged. And the series converge. And the sum of this series will not greater than the norm square of F. Okay, so this is the Bessel inequality we just proved. And now we introduce some geometric notation. Suppose Un is a sequence in X, and U is a point in X. As in Euclidean space, we can define the Un converge to U if the distance from Un to U goes to 0. That is, we use the norm A minus B. We denote we call the distance the norm of A minus B to be the distance of A and B. Okay, so this is distance as in Euclidean space. So if the distance from Un to U goes to 0, we say that our sequence Un converges to U. And if for some S in X, the partial sum of a series, so this is a sequence denoted by Sn. If this sequence converges to Sn, for a sequence Un in X, we take the sum. This is a new sequence. Sn, this is a new sequence. If this new sequence converges to some point S, we say that the series converges to S, and write S equal to the sum okay. So this is the convergence of a series. Now, we introduce the abstract Fourier coefficients and the Fourier series in a space, in an inner product space. Let EI, I from 1 to infinity, be a also normal system in X, and F is an element in X. So we called the inner product of F with respect to EI the I's Fourier coefficient of F with respect to the orthogonal system, orthonormal system EI. Then using the Fourier coefficients, we can construct a sequence, a series. This series is Ci EI. We can construct this series. This series, we call this series the Fourier series of F. This is the Fourier series of F. And we write F using this notation to indicate that the series on the right is the Fourier series of F. Okay. So we know that the sum of Ci square will not greater than the norm of F square by Bessel inequality. Okay, so this means that the left hand side is convergent series of real numbers. So by calculus, we know that Ci converges to 0. That is, the Fourier coefficients must converge to 0. Okay. We also emphasize that the Fourier series need not be converged. Need not converge. If it converges, it might converge to points other than F. Even if it converges, the sum might not be F. Okay.